Alright, here we are again. Now it is time to learn about the relationship between load, shear, and moment, and in particular, learn how to create shear and bending moment diagrams by the method of integration. And this is lesson 24. Now, a bit of business. On the previous lecture, I've noticed that there is a slight error. I didn't have this x in this equation. We did have it when we developed it, I believe, back previously, but there is an x that didn't get transcribed properly here. So be aware of that. And next, so I'm going to give you the formula for load, shear, the relationship between load, shear, and moment. However, I think I could develop them, I could go through the full derivation, but I think I'm just going to put up a nice handout showing the development of that, the proof of that, but you can also either see it in the book, or I think I'm just going to put this handout on Blackboard. So there will be a, if you're curious where these equations that I'm going to use come from, feel free to check out Blackboard, and it goes through the full derivation. Okay. So let us look at the relationship between load, shear, and moment. Relationship between load, shear, and moment. Load, shear, and moment. So, you can see the handout that I will post for the full derivation of this, but the basic idea is this. V of x is equal to the negative integral of w of x dx, and m of x is equal to the integral of v of x dx. Or we could also express this as or w of x equals negative dv of x over dx, and v of x is equal to dm of x dx. In other words, moment is the integral of shear, and shear is the integral of moment, shear is the integral of load. Or you can think of the distributed load W as the derivative of shear, and the shear as the derivative of moment. Now, we do need to be mindful of the fundamental theorem of calculus. Fundamentally, what this means is, if you remember your calculus, you will say that look at this, moment of x is equal to the integral of shear of x. Shear is a function of x. So this doesn't mean that the shear is, the moment is simply the shear. That doesn't, the actual value does not, you cannot get the full value of the moment function out of the shear function. Because if you remember from integration, you'll always have that plus c at the end. Every time you take an indefinite integral, you're always going to end up with a plus c at the end. So really what this integral tells you is that the integral of shear tells you the change between 2 points. The change in the moment between 2 points. In other words, we can think of this as, another way to think of this is that the v of b minus v of a is equal to the negative integral of, from a to b, of w of x dx. So again, this is just a calculus thing. When you integrate, you don't actually get the final value of the function, you get the change in the function between the two bounds of integration. And the same thing here, this is just calculus. So m of b minus m of a, again, is going to be equal to then the integral from a to b of v of x dx. So we're going to need, this is a differential equations thing, you're going to need some boundary conditions, and we'll be looking at that as we go forward. Also, another note, note this negative w of x, we are assuming that w of x is downward. W of x assumed downward. And that is because in almost all the cases, especially civil engineering, in almost all of our cases, when we have loads, the distributed loads are almost always pointing downward. It's very rare that you're going to have an upward distributed load. It's not uncommon to have, it's actually fairly common to have negative moment, but you can actually end up with, if you study more beam theory, you'll learn that you can actually have negative moment from downward. You can have negative moment from positive distributed load, essentially, when a beam goes into double curvature. But it's very, very rare that you will have upward load on say a beam. There are a few cases we could think of. We could think of, say, I don't know, a vessel that had negative pressure in it or something like that. Or I'm sure we can sit here all day and contrive all sorts of examples that could happen, but it's going to be fairly rare. In almost every case, a floor system, a beam, a building, you're going to have far more downward loads than upward. Although one very major example I'm aware of in civil engineering is wind load on roofs. Oftentimes you do end up with a upward load from wind on rooftops. So that's probably the biggest example from civil engineering that I'm aware of that you're likely to encounter negative distributed loads. But anyway, so if we use what this comes to, if we use negative W of x, then this comes to the integral of negative W of x dx. So it would actually end up with a positive shear, etc. Okay. So you have the equations, and again, see Blackboard for the actual, the full derivation of this. But then I think I'm going to illustrate the method of integration via simply a long form example. And that's really all I'm going to do to illustrate this. Okay. So let me show you an example here. This is going to be another beam, and like a lot of the beams I work with, it's going to be a nice friendly beam, a nice friendly simply supported beam. That's my favorite type of beam. Just like one of my favorite type of members is CAL members. They're nice and simple. Because I'm just a simple person. Okay, anyway. So, let's say I have points A and B here, and then I'm going to have a distributed load here. But I'm going to make this interesting, and I'm going to make it a triangular distributed load, like so. So this triangular distributed load, it starts up at 4 kips per foot, and then it linearly decreases down to 0. Okay? So I'm given this, and I'm also given that I know the length of this thing is, let's say, 18 feet. And I wish to find V and M by inspection. Or sorry, not V and M by inspection, just find V and M functions. Find shear and moment functions. And we're going to do this by integration. V and M functions. Now let me show you the loads on here. Sorry, not the loads, the reactions on here. Obviously AX, AY, and BY. Now it's, I think, you know what, just for fun, I will go through finding the reactions on this thing. To find the reactions, I'm going to recognize that this is equivalent to, I have an equivalent point load 1/3 from the side. That's going to be 1/2 times 18 times 4. Just the area of a triangle is 1/2 base times height, or 36 kips. So this is not an actual load, this is the equivalent point load. And if you remember from statics, you cannot use equivalent point loads to find shear and bending moment diagrams. The only thing, only thing you use equivalent point loads for is calculating reactions. So carve that in stone, Remember that. Only use equivalent point loads to find reactions. That is it. Nothing else. You only use equivalent point loads to find reactions. To find reactions. They're good for nothing else. But that's still a pretty good thing. And then this is going to be at 6 foot from the left. It's a nice color. It's almost a maroon. Anyway. Okay. So let me find the reactions. This is going to be fairly simple. So the solution. Let's get the reaction. I think I have enough time for this. So let me do the sum of moments about A is equal to 0. And this is going to be equal to negative 6 feet times 36 kips plus 18 feet times by is equal to 0. And this leads us inexorably to by is equal to 12 kips upward. And then AY, if I do a sum of forces in the vertical direction, is equal to 0. I'm going to get that AY minus 36 kips plus 12 kips equals 0, or AY is equal to 24 kips vertical. So now I have my reactions. Now, thankfully, on this particular beam, I have no discontinuities, if you notice, except for at the edges. So I can actually get away with using a single moment function and a shear function to describe these things. Again, this point moment, I cannot talk. This point load is not a real load, it's just the equivalent point load, the centroidally equivalent point load used for finding reactions. Now, so all I really need to be concerned with is the distributed load in the red here, not in the maroon. And since I don't have any discontinuities, I don't have to worry about it. This is great. But if I did, then I would need to worry about things. Okay. Let's see. So let's do this. So what I need to do is I need to, so I have my reactions. So let me label that as step 1, reactions. 1, reactions. 2, develop the load function. We need to develop the load function. In other words, before I can integrate a W of x, I need to actually get a W of x. I don't have a W of x like get. Well, this is fairly simple. I know how to, I took Algebra 1. I remember taking Algebra 1. So I know how to find the slope, I know how to find the equation of a linear line. Because I took Algebra 1. I did alright in it, so I learned how to find linear equations. So high school wasn't a complete waste. Linear, y equals mx plus b. I guess that was actually in middle school, wasn't it? Anyway, whatever. It was a long time ago in a galaxy far, far away. Okay, so I know that it's y equals mx plus b. If you do not know how to find this, oh boy, if you don't know how to find the equation of linear line, you're in the wrong class. Okay, so slope m, that's going to be fairly simple. It is just rise over run, remember that, negative 4 kips per foot over 18 feet. It's actually going to be a negative 2 over 9 kips per foot, or kips per foot squared. So it's a rather interesting unit system. And the intercept, your b, is going to be then, this point over here, this height over here, 4 kips per foot. So thus, our overall, so combine these together, we get that our overall w as a function of x is going to be 4 minus 2 over 9x. That is our w function. And that is what we're going to be integrating. Okay? So next, I want to develop the shear function. I have my w function, now I need to develop my shear function. Shear function Alright, so let's do that. Well, v as a function of x, again, is equal to the integral of negative w of x dx, which is equal to, let's see, so it's going to be equal to negative 4 minus 2 over 9 x dx, or if you take the integral of that and distribute the negative, etc., etc., I don't think I need to tell you how to integrate a polynomial, x squared over 9 minus 4x plus a constant, but I'm going to call this c1 because we're going to have another one for the moment. So, and again, the reason we have this c is because this is an indefinite integral. Always forget the plus c, don't you? Okay. Now, we need to get rid of this c. I actually want to have a function, I don't want a c in my function. So what I need is, I need a boundary condition. And what might that be? Well, I happen to know that I do know one value of the shear. V at x equals 0, the shear at x equals 0 is going to be equal to 24 kips. So notice, for example, look at this point here. Look at this previous example. When we had the reaction, the upward reaction on the left here, our shear diagram immediately bumped up 18 kips. So that should be a hint. When you have a load, a point load pushing upward, that's going to cause your shear diagram to do an instantaneous jump. So the shear diagram will jump up by the amount equal to the reaction. So I would know at this one, a boundary condition for this one would be that the shear at the left point at x equals 0 would be 18 kips here. But in this example, it's 24 kips. So that's going to be a boundary condition we can use. Not too bad. Oh, sorry, did I? Yes, yeah, 24 kips. Yes, that'll work. So simply solving, we just simply substitute this in. So I say v of 0 equals 0 minus 0 plus c1. Thankfully, a lot of this stuff just cancels out. Equals 24. And this leads us to c1 equals 24 kips. So finally, v of x is x squared over 9 minus 4x plus 24, all in kips here. And that is our equation for shear at any point along the beam. And notice, this is a parabolic function, and the load is a linear function. So in general, if you have a polynomial of any, so if you have a loading that is polynomial in any form, the shear is going to be one order higher. So if this is linear, if your load is linear, your shear is going to be parabolic, and your moment would be is going to be a cubic function. If load was constant value, say just a constant w across, my shear is going to be a linear function, and my moment is going to be a parabolic function. This is why we had a constant load here, and we had linear functions for our shear, and we had parabolic functions for our load. This is an integral relationship. So finally, I want to get the moment function. Well, I guess I still have another step after this, which is actually graphing these things. So let's do that. Moment function. Moment function. And this one's going to be fairly straightforward. I know how to integrate polynomials. Hope you all do too. m as a function of x is the integral of v of x dx, which equals the integral of x squared over 9, so just plugging in the shear function into the moment equation, x squared over 9 minus 4x plus 24 dx, and this is then equal to x cubed over 27 minus 2x squared plus 24x plus c2 here. So we have another constant. I just called it c2 because it's a different constant than the other one. And I need a boundary condition. However, this one is very trivial. Every time I have a pin, every time I have a pin or a roller, I'm going to need a moment of 0. That's going to be a boundary condition. So boundary condition, m at x equals 0 is 0. So this is fairly straightforward from here. I'm going to have m as a function of x is just x cubed over 27 minus 2x squared plus 24x, and that's it. My c just drops away because it's 0. And that is my moment function via integration. Oh, I don't like how that looks. I want that to be very clear. That's a cube, not a squiggle. Oh, and I lost part of my box. Here, like that. And then finally, for my last step, I'm going to plot the results. So 5, I'm going to plot the results. So if you're asked for shear and bending moment diagrams, what you're really after is these plots at the end. But you will often need to find the functions in order to create the plots. So graph results. I'm going to start by graph. I like to plot these directly above each other if I have space. So that's why, even though I could fit part of it below here, I didn't. I like to plot them, the load, the shear, and the moment directly above each other if I can, because that makes things very clear and makes the geometric, the shear, load, and moment relationships very clear if you can plot them directly above each other. And also in the next lecture, when we learn how to do shear and moment diagrams by inspection, you'll definitely want to plot them above each other. So this is linear, like this here. 4 kips per foot, 24 kips here, and 12 kips here. And then here I'm going to have, so this is my loading, or my free body diagram, if you will. Then I'm going to have my shear function, my shear plot, or the plot of my shear function, which is going to be v in kips, and it's going to look something like this here. So it's going to jump up to 24 here, and this is going to be parabolic. It's going to have a peak. It's going to basically be getting a gradual. It's going to have a gradual decrease in slope. The slope is going to peak here, but then it's going to gradually sort of shallow out here. Let me think about that just a second. Yeah. So it's going to be steepest here and shallowest here. Oh, I don't like how that looks. I want something more like this. And it's not half bad. And this is here, -12. And so this is going to be positive shear, and this is going to be negative shear. And this does actually correspond to our state of stress shears that we're familiar with from previously in the class. So let me draw some little elements here. This is your, like here, like that, positive shear, etc. here. And then, well, actually, maybe not. Sorry, I shouldn't say that. This is the stress triangle, stress square that we would have and from the positive state of shear stress, with the convention that we saw earlier. So don't confuse this element with what we've seen in previous portions of the class. So this is negative here, which if you would have a downward arrow here and upward arrow here, which would mean you would have on the sides like this and like this here. And we do need to be aware, or we need to be cognizant of the derivative relationships here. So we do need to remember that the dv over dx is negative w of x, or dm of x, or dm over dx is equal to v of x. So, in other words, when w is 0, this is, so you might be wondering, how did I know this? The slope of this would be leveling off here? Well, again, the load function is the slope of our shear. So notice the load down here is 0, or the distributed load w down here goes to 0. So the slope of this shear graph must be coming to 0. And then, since the v of x is the slope of the moment graph, whenever my shear crosses 0, I must have a local maximum or a local minimum in my moment graph. Again, this is just a calculus thing. So then, here, I'm going to plot the moment, m kips, here, and I don't have the number in front of me. To find the maximum, it wouldn't be that difficult. But anyways, it's going to look something like this. It would actually be a third order equation, a cubic equation, but it would still look something like this. So this is going to be positive bending throughout. This is positive moment throughout. And M max is going to be directly below the point of 0 shear, so M max. So I don't have numbers on this one, but it wouldn't be too hard to calculate them. Alright, oh, a little error in my units here. Moment is definitely not in kips, it's in kip feet. Kip feet. And then finally, I just want to give a few more notes on this. Note, we still have to write new equations every time the load function changes. Still have to write new equations. So we're not using the method of cuts, but we still have to write new, but instead of taking a new cut every time there is a discontinuity, we have to write a new equation every time there's a new discontinuity in the load. Write new equation anytime the load changes. The load changes. The load changes. In other words, say like a new boundary condition, you get a new boundary condition, but we keep the x origin the same. We get a new boundary condition, but we keep the x origin the same. So, again, what this would do is that your, if we had our, let's say our, let's look back here. There were no discontinuities. But say I had a point load here. I just put a point load somewhere in the middle. This would not change my actual load function W. My load function W would stay the same, but what would happen is I would have in the second zone here, I would have to use a new boundary condition. And that new boundary condition would basically be the shear would be modified by that point load at the end point there. Okay, hopefully that is illuminating a bit for some things. I think that'll do it for today. I just wanted to introduce shear and bending moment diagrams. We will be covering a third technique, shear and bending moment diagrams by inspection, on Monday. And again, for students this semester, the exam will be this evening, 6 to 9 p.m. Hope you're prepared. If you have any questions on this, feel free to email me. I'm always available. And as always, thank you.